Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. This is a series of videos for Thermodynamics 1 for chemical engineers, and we are looking at Chapter 4, which is over entropy. In our last lesson, we talked about reversible and irreversible processes, and we need that so that we can define what entropy is. So entropy is a thermodynamic property in the simplest sense. It's just a property. The name for this was selected by Rudolf Clausius in 1865. Now you probably know that name Clausius, right? We run into it in some other places. But it means transformation, and it sounded a lot like energy, and so therefore he thought that was nice because it's sort of a counterbalance to energy. Kind of in the same general time period, Ludwig Boltzmann in 1877 began relating this entropy to the way the molecules were configured in a fluid and started the basic concepts that became statistical mechanics. The idea is that there are a lot more ways that you can be disordered than you can be very neat and ordered, okay? So disordered is high entropy, ordered is low entropy, okay? Fewer ways to do it, lower value of entropy. More ways to be disordered, higher entropy. Now we are going to define entropy as simply a state property, which, if you'll recall, means that it is path independent. So it is something that is sort of possessed by a fluid at a particular condition. But we are going to define it based on a path, and it's an impossible path. We're going to define it based on a reversible path. So entropy is a state property, right? So it only depends on the state, so maybe temperature and pressure. Also, it is going to be unchanged for the universe whenever there is a reversible process. And as far as the universe is concerned, it never decreases. It can only go up, meaning things can only become more disordered. It will increase for the universe whenever there is an irreversible process. So no change for reversible, an increase for irreversible. So ds is not path dependent, but we are going to define it based on a path dependent process, a reversible process, and we're going to look at the change in that heat transfer, so how much heat is transferred, divided by the temperature that transfer happens at. And so we can integrate this over the beginning to end of a process and get a change in S. So S for the final state minus S for the initial state. And that's going to be the integral from the initial to final value of the change in heat transfer per temperature. Okay? And again, this has to be positive or zero. Zero indicates reversible. Positive indicates irreversible. And if you ever come up with something that is negative, that's going to be impossible from the point of view of the universe. So what is the entropy change of the universe? Delta S for the universe is going to be the entropy change for our system plus everything that's not in our system, which is the surroundings. So the sum of those two delta S's will be the delta S of a universe. And in order to kind of understand what this really means, what the implications are from this, it's kind of nice to look at some special cases and draw some understanding. So we're going to look at three that are particularly useful. We're going to look at a reversible adiabatic closed process. So reversible, remember, means that it can go forward or backward without any additional energy input. Adiabatic means there is no heat transfer at all. And closed means that the mass is going to stay in the system. An irreversible adiabatic closed process is the second one we're going to look at. And then we're going to look at something called the Carnot cycle. Let's look at this for that reversible adiabatic compression or expansion, either way, but we're going to have a change in the volume of a closed system. If we look at the system itself, we defined entropy is delta S for the system is going to be the final minus the initial entropy, or the integral from the beginning state to the final state of ds for our system. But we know that that is by definition, and I can put 3 lines there indicating it's by definition, is the change in Q for a reversible process going through this divided by the temperature that it occurred at. And so if I just only knew what dq reversible would be, but I have assumed that this process is adiabatic. So therefore, reversibly or irreversibly, dq is going to be 0. Therefore, delta S for this system has to be 0. Now, we are going to kind of learn from this often. If you have this combination of reversible and adiabatic, whenever you see those, if you look at this definition here, it always means that it is isentropic. So delta S is equal to 0, or S1 equals S2. So this is going to be something that may not look too significant now, but it's going to be a very useful fact to remember. Whenever you see reversible and adiabatic, it is isentropic. And any 2 of these words actually imply the third. So if you had reversible and isentropic, it would have had to be adiabatic, etc. Now, let's look at the surroundings. The definition is going to be the same, but Q for our system is the opposite of Q for the surroundings, right? If it comes or goes from the system, then it's doing it to or from the surroundings. And we just said that's equal to 0. Therefore, it's got to be that delta S for the surroundings is also 0 using the same logic and definition. If we combine these, therefore, delta S for the universe is delta S for the system plus delta S for the surroundings, which is 0. So delta S for the universe for a reversible adiabatic process with a closed system will be 0. What if we now look at an irreversible, not adiabatic expansion or compression for a closed system? And we are, for the sake of simplicity, we're going to fix it so that we can compare a reversible and an irreversible process for the same initial and final state. But I'm going to require that the amount of heat transfer be the same for both of those. Now, we will be proving this later, but a reversible process will produce the maximum amount of work possible, or if it requires work, it will require the minimum work possible. And we will be somewhat proving this soon, but we can do this through an energy balance, and we will soon. But a reversible process is going to produce the maximum and require the minimum work possible. As we said when we were defining this and talking about the work that Clausius and Boltzmann did, it's going to produce the optimal path, this reversible assumption. So let's consider a system, okay, here's my system, and one where we are doing work input, okay? So work is going into the system, okay? Work, in this case, using our sign convention, is positive, and in this case, the reversible work is less than the irreversible work. If I flip and look at the other case where we are taking work out of the system, our work is negative and the reversible work in value is greater than the irreversible work in value, okay? So irreversible is going to be produce less work, okay? But if you think of it with the signs, then we end up with the reversible work is less than the irreversible work in the sense of signs, okay? And again, this is the work convention that work in is positive. And if we combine this with the first law, we can do this for the two cases, reversible and irreversible. So delta U for the reversible is Q for the reversible plus the work reversible. And delta U for the irreversible is Q for the irreversible plus the irreversible work. All right, no surprise there. But we have fixed the amount of work, so therefore these two here are going to be the same value. What we also know, we just said that regardless of whether it's in or out, if we use signed values, the reversible work is less than the irreversible work. If Q reversible and Q irreversible are the same, then this requires that delta U reversible must be less than delta U irreversible. Okay? We have previously defined that delta U is the integral of CV dt. What if we start at T1 and look at what the final temperature would be for this reversible process and this irreversible process? If I do this for delta U for the reversible process, it's T1 to T2, and this is T2 reversible for C time of C sub V dt, okay? And then I know that this has to be less than delta U for the irreversible, which is T1 to T2 irreversible of CV dt. Now CV is not going to change because the process changes. It's just a property of the material. And if this on the right is greater than the one on the left, and we know that temperature must be positive and CV must be positive, then what we find is that the only way for this to happen, for CV and T to all be positive, requires that T reversible, the final temperature reversible, must be less than the irreversible. So there would be more temperature change for the irreversible process. And a lot of times we think of that as the result of friction, right? If you rub your arm really hard, briskly for a while, it's going to feel warmer, right? And so friction, we know one of the things it does is warm things up, change the temperature. And we have gotten that result based on our definition of entropy here. This concludes our initial examination of entropy. We're going to need to keep looking at this quite a bit more to really have a full understanding of what entropy means for us. But we will be looking at that again in our next lesson. Thank you very much for your time.